Okay, so today we're going to talk about continuous random variables. Last time was about discrete. This is continuous, so you need to already be thinking about the curve and all the area that's underneath the curve when we're talking about continuous. Distance traveled by a car using a gallon of gas, waiting time at the checkout counter, amount of water released through the Hoover Dam. All these things are fluid measurements. So it's all continuous. All that's easy and stuff you already know. Here we go. The graph in figure 17 gives the distribution of the yearly amount of rainfall in Rainy City. In a randomly selected year, we want to know what is the probability that Rainy City got more than 8 inches of rain. What would you do? 8 inches of rain. Look down here. First, you're going to state what it is that you're finding in words. Then you're always going to state the piece, turn it into math. Well, if this is more than, and this is more than or equal to, isn't it? Okay, no, it's not. Why is it not equal to? There's no equal to here, and there's no equal to here. Why? Because for binomial, somebody had to have the equal to. Why do we not have the equal to here for continuous? Because the area of one slice of the curve is 0. If you have a cake and you cut the cake, is there any area of cake in your cut? No. So that's why with continuous, with the curve, you don't have to worry about any equal to's. So the probability that x is greater than 8 is the same as 1 minus less than 8. So why do I have to translate it into this? Because look at what I was given. I don't know what it is above that. I mean, I guess I could. I don't have anything to add together. So what do I need to do? Yeah, I got to add all these together, and I got to do 1 minus them. So that's what we're doing right here. 1 minus less than 8. So there they are, and there's my probability. Okay, what's the probability that Rainy City got between 2 and 6? So again, you're stating what it is in words, you're stating what it is in math, and then you're just adding those two pieces together. All right, check C out. The probability that we got exactly 2 inches of rain. Why is that 0? It's a slice. It's a slice, and there's no area unless we have 2 slices. Rainy City got at most 6 inches of rain. That's less than or equal to 6. So I'm just adding those 3 pieces up. All right, then we get into the normal distribution, and this is something that I didn't do very often, but to describe a normal distribution, they go in for normal, and then they're going to go parentheses, and then they're going to say like 27,3. That means that it's a normal distribution with a mu of 27 and a standard deviation of 3. So if you see it written like that, that's what that means. The first number is your mu, second number is your sigma, and this big N is telling you that it's normal. Who is that? And don't say Z. But he is the standard normal distribution, which tells us how far away something is from the mean. It standardizes everything. Do you remember we did a problem where it was like in Hope's chemistry class, she made an 83. And in Kyla's biology class, she made a 74. But then it gave the average and the standard deviation for both classes. And it turned out that Kyla actually did better relative to her class because the average was way lower in the standard deviation. She was like 3 standard deviations above the mean, where Hope with her 80 whatever could be below the standard or could be below the average. So it makes things all relative. It's standardized, levels the playing field. And where is this formula? Where on the formula sheet? Oh, come on. Top, back. Top, back. Yep. Equals statistic, that's x, minus parameter, that's mu, over standard deviation of statistic. Okay, it's called the z-score, and we'll practice finding all this stuff. Okay, let's talk about properties of the normal distribution. First of all, it's continuous. It is symmetric about the mean. It is bell-shaped or mound-shaped. If they give you choices of what normal distribution, could it do that? Oh, we don't know. Is that a normal distribution? When you draw your curve, is that how you draw it? Absolutely not, because where's he going? Yeah, he's going to hit that line, and the curve approaches the baseline, the horizontal axis on both sides, but it never touches it. And so that's why it says it's got to have a bell shape, because this right here never touches. Because there's always that, and I call it the 10-pound rat. If you do like a, if you gather data about the rats in New York City, and you do their average sizes and the standard deviation, let's say the average weight of a rat in New York City is 3 pounds, with a standard deviation of like half a pound. Well, that means that 99.7% of my rats are within 3 standard deviations of my mean. And if my mean is half a pound, if my standard deviation is half a pound, how far are we going? 1.5. So where are we? 4.5 and 1.5. But these never touch. And the reason why is somewhere there's a 10-pound rat. Or somewhere there is a 0.2-pound rat. There's always the exception to the rule, and that's why this never closes off, because it leaves open the possibility of that crazy outlier. And here we go, nearly all of the distribution, and you know that means within 3 standard deviations, 99.7% of our data lives. But that's not 100%, and that's why it doesn't. That's why it doesn't touch. Now, this we're solid with. That's what makes it symmetrical. This, and I think we had a conversation about that the other day. I said the normal distribution doesn't tell you anything about mode. Guess what? On a normal distribution, the mean and the median and the mode have to be equal. All right, using the normal distribution table, here's your 68% within 1 standard deviation, 95% within 2, and 99.7 within 3. What is this example 15? How far back is that going? Is it to the rain? No, that's 14. That's it? There's no example? There's no words? Oh, it's not a situation. Okay. All right. So if I wanted you, yeah, and these are Z's. So when you normal CDF them, you got your lower and your upper, and your mean and your standard deviation will be 0 and 1 because we're Z's, right? And that's the standard normal distribution. You're going to use the 1E99 for infinity or for negative infinity. What about this one? Find the 95th percentile of the standard normal distribution. I want 95% of the cake. So what do you do there? Do you normal CDF it? No, you inverse norm it. And when you inverse norm, who is he? Always area to the left. Always, always, always. So what if it said, I want you to find me the top 5%? What is the cutoff for the top 5% of SAT scores to get into Harvard. So you would inverse norm 0.95, and then you would need the mean and the standard deviation. Okay. Then this is just walking us through all that, which we've already talked about. Anytime you do a normal distribution on a free response, you will always what? Draw the graph and shade and label. Always draw your graph. Still cruising. Here we go. The normal distribution as a model for measurements. Example 17, at the end of the semester, a teacher determines the percent grade earned by students, taking into account all homework, tests, and project scores. These student scores are normally distributed with a mean of 75 and a standard deviation of 8. If a 90, 80, 70, 60 grading scale is used to determine the letter grades of students, what percent of students earned an A? So, you should see your curve, and you're chopping it off at what? 90. And an A would be which way? To the right. So I'm going to normal CDF it because I want to know how many, what percent. So I want to know how much cake. So how much cake is in here? So normal CDF. Now, I'm going 90 to 100. Why? Technically, grades can't go above 100. And then I got my mean and my standard deviation. Type that in, and I got 2.95% got A's. Not 2.95 kids, 2.95% got A's. Okay. If the same scheme is used to determine the letter grades of students, what percent of students earned a B? Okay. What block are we talking about for a B? From what to what? From an 80 to an 89. So I'm going normal CDF from an 80 to an 89 with my mean and my standard deviation. 22.6% got B's. Is it logical that that percent is bigger? Why? So? Uh-huh. Give me more. Think about the curve. It's closer to the mean, so yeah, there's more area there. You get up here on the tail, that's a smaller piece of area, so it absolutely makes sense that that's where the bigger piece of area is. So it makes sense that that number's bigger. If the teacher decides to give A's to the top 10%, what are you doing now? Inverse norm, because I just told you how big of a piece I want. I want 10%. I want 10%. I want to know where to cut it at. Well, when you inverse norm, it's always area to the left, so that's why I have a 0.9 there. With my average and my standard deviation, I need to cut it at an 85.25 if I need 10%. Let's say I work in a college and they say, your department, you have to have 10% A's. So then that tells me where to adjust my scale. If the teacher decides to give B's to the next 20%, okay, what would you draw? But what would you draw? That's what you would type in your formula. What would you draw? The 10% to the, or B's to the next 20%. What did we have first? We had 10% that were A's. I now want this to be 20%. So how do I know how much area that is? 100 minus 10 minus 20. But guys, they want, if this is a free response, they want to see that. They want to see that drawing. Especially if you've got a free response that's very number crunchy and very formula, you got to find a way to dress it up. So draw, absolutely. So that's why I have 70% here, and there's my mean, and there's my standard deviation. And that gave me this bottom number. Where'd he come from? Yeah, the problem before. And again, that's another great example of how part A, B, and C kind of build on each other, and you use information you've already found. All right, are we good? Okay. So we've talked through all this work. So now let's go here. So this is talking about combining independent random variables. So sometimes we're interested in the linear combinations of independent random variables. If we know the mean and the variance, not the standard deviation, of the two random variables, we can determine the mean and the variance of linear combinations. So that's talking about addition and subtraction and even some multiplication. So we've got x is a random variable with a mean mu sub x and a variance of sigma squared sub x. So his standard deviation is sigma sub x. Then we got y, which is another variable, and he's got a mean of mu sub y and a variance of sigma squared sub y. So here we go. Now, in a word problem, are they going to give you variance information, or are they going to give you standard deviation information? I mean, look, think about the problem you just did. They're going to give you standard deviation information. It's your job to know that you've got to turn that into variances if you've got to add these together. So if I take any variable and I want to multiply it by something, I just multiply the means. Now look what you do to the variance. Do you just multiply the variance by a? What do you multiply by? A squared. Okay, but talk to me about what that would do to the standard deviation. Let's make another column. What would that do to the standard deviation? Be the same as what? A sigma. So when you multiply all of your data by a certain number, and I think in that G problem we were talking about, it was if he goes and charges, if he goes for this many miles or whatever, and let's say he charges $5. So now we're going to multiply all his people by $5 because we're trying to see how much money he would make. You're just going to multiply that by your mean, and you can also just multiply that by your standard deviation. If I want to add something to it, for this excursion we're going to go on, if you'll pay an extra $5, I'll give you a water bottle and I'll take a picture of you. So I'm just going to add that $5 to it. And does that change your variance? Because what am I doing to all the costs? I'm adding $5 to everybody, so it doesn't change the spread at all. So what's it going to do to my standard deviation? Yeah, not a darn thing. Okay, and then here they go with a little combo. Okay, so now let's multiply it by something and let's add something to it. So both of those affect the mean. But which one of those is going to affect the standard deviation? Just the multiplication. How? A sigma. All right, now we get to the good stuff. Let's say I have two separate variables. So I have this Jeep excursion over here, and then his sister does a canoe excursion in Colorado. And I just want to find, for some reason, the sum of their average. All I got to do is add their two averages together. AP test, is not ever going to ask you, what's the sum of their variances? What are they going to ask you? What's the sum of the standard deviations? So you've got to remember that there's no relationship between the two standard deviations. Standard deviation of the total does not equal the two standard deviations added together. The variances are related. So how does that translate over here? I don't want sigma squared. I want sigma. How do I get sigma out of this? Square root it. But you're square rooting the sum of the variances, not the sum of the standard deviations. Okay, here's another one that's really interesting. I remember us going over this. If I want to subtract two variables, then I can just subtract their means. Totally fine. What do you do to find their standard deviation? You're still adding it together, even when it's subtraction. Okay. Now, if I'm going to multiply them by something and add them together, then that's exactly what I do to my means. But for my standard deviations, and remember this one, when they were squared, we just went ahead and square rooted both of them, right? Can I do that here when they're added together? No. So this is the square root of a squared sigma squared x plus b squared sigma squared y. And then this nice little footnote, if x and y are normally distributed, then any linear combination of the two of them, whether you want to add them or subtract them, that distribution is also normal. Okay, this is a fantastic example. Y'all ready? A company markets 16-ounce bottles of jam. The mean amount of jam per bottle is 16 ounces, with a standard deviation of 0.1 ounces. The mean weight of the glass bottles holding the jam is 5 ounces, with a standard deviation of 0.5 ounces. Can we just take all that information and stat that up? Can we do that? Okay, so off to the side with a pencil or a pen, I'm going to declare my variables. So x is going to equal jam, or you could do j if you wanted to. Y is going to equal bottles. And W is going to be the jam in the bottles. Okay. Then I know that mu sub x, the mean of the jam weight, is 16, are these ounces? Yeah, 16 ounces. With a standard deviation, that's a sigma sub x is 0.1. And then I have my information for the bottles. So I'm just taking all of the words and I'm statisfying it. Statistically fying it. I'm turning it into stats. Getting it out of English. Okay. And don't just sit here and copy stuff down. We're going to go through this one thing at a time. So is everybody with me to here? Okay. So part A. What is the mean weight of a filled bottle? So I want mu sub W. I want a bottle and jam. Well, mu sub W is going to equal what? Mu sub X plus mu sub Y. So I'm going to write that out because I'm writing my formula. You guys getting all this? Okay. Then I'm going to plug in my numbers. So mu sub W equals 16 plus 5, 21. Slap the word ounces on it. Make it make sense. What is the standard deviation of the weight of a filled bottle? Okay, here we go. I want the standard deviation. I don't want the variance. I want the standard deviation of a filled bottle. So that's W. And that will equal the square root of the variance of the jam plus the variance of the bottle. Remember, standard deviations are not related, but the variances are. Now, why is that under the square root? Exactly. I want to find the standard deviation. I do not want the variance. So then I fill my numbers in, and I get 0.51 ounces. So do you see how this gets worded and how you need to write it and the formulas and everything? Okay, now part C, they're going to crank it up a little bit. When shipped to stores, 12 random bottles are packed in a box. What are we doing now to the weight? Multiplying it by 12 because I have 12 of them. What is the mean and the standard deviation of 12 bottles? Okay, so I've got G, a new variable, and I define G as 12 full bottles. The mean of G equals 12 times the mean of W. Who is W again? The jam and the bottle. So now I have 12 of them. So that's just 12 times the mu, so 12 times 21 is 252 ounces. Check this one out. The standard deviation of 12 full bottles is the square root of a squared, 12 squared, times the standard deviation squared of the filled bottles. And then I plug my numbers in and square them and multiply them and square root them. And I get the standard deviation to be 6.12 ounces. How's that sitting? Everybody okay? Okay. Now we got to box them up. The mean weight of the empty boxes is 50 ounces with a standard deviation of, I just lost my place, of 4 ounces. What is the mean weight and the standard deviation of the weights of the filled boxes? Okay, so what's in the box? More specific. 12 jars of jam. I have jam, they are in jars, and I have 12 of them, and they're in a box. I got it? Sounds like a Dr. Seuss book. All right. So, more letters. We're going to let B be a box that's packed, and E be an empty box. So they want mu sub B, and they want sigma sub B. Well, the average of a box that's packed is the average weight of an empty box plus, who is this guy? Who's mu sub G? 12 full jars of jam. The jam in the jars, and I have 12 of them. That's that guy. Well, they told me that the mean is 50. I found that the mean of 12 jars of jam is 252, so that's the mean of a box packed with jam in jars, and there are 12 of them. 12 jars of jam, not 12 boxes. To find my standard deviation. Does everybody agree I don't need to multiply anybody by 12? Because I've already done that, right? So I want the square root of the variance of an empty box plus the variance of 12 jars of jam. Throw my numbers in here, And then do a little calculator. Okay. Last question. If the amount of jam per bottle, the weights of the bottles, with the lids by the way, and the weights of the boxes are all approximately normally distributed, all three of those distributions are separately normal, what percent of boxes, what should you automatically think when you see the words what percent? The curve and what command on your calculator? Normal CDF. I want to know, how big is the cake? How big is the piece of cake? What percent of boxes will weigh more than 320 ounces? Okay. What's my mean? And I want 320. So do you see how I'm writing what I want? Then I come down here. He's 320, and I shade. Always draw, always shade. So I'm going to normal CDF from 320 to infinity with my mean and my standard deviation that I found before, and I got 0.0069. Which means, and here's my nice little sentence, 0.69% of the boxes will weigh more than 320 ounces. Okay, so now let's talk about sampling distribution. What is a sampling distribution? Exactly. You have a bunch of samples, which means you have a bunch of means. I'm putting them all together, and I have a distribution of all of their means. The sampling distribution is the probability distribution of a statistic. Different samples of the same size from the same population will result in different statistical values. The standard error is the standard deviation of a statistic. Fun fact, I thought this was interesting. Parameters are usually represented by Greek letters and statistics by Roman letters. What's a parameter? Information about the population. What is a statistic? Information about the sample. All right, remember good CLT? Love some CLT. All right, central limit theorem. Regardless of the shape, if a large number of samples are taken from that population, then the distribution of the sample means will be approximately normal. What's the magical number? 30. N has to be greater than or equal to 30. 30 is fine. It's not fantastic, but it is fine. Okay, then, do you remember you've got mu sub x bar? If you have information about a whole bunch of means and you write mu sub x, you will lose points. If it's a bunch of means, you have to put mu sub x bar. This is one sample, the mean of one sample. This is the mean of the means of a bunch of samples. And then this guy's on your formula sheet. Why don't you find him? Get your eyes on him. On your formula sheet. Is he front, right, towards the bottom? Yeah. If x bar is the mean of a random sample of size n from an infinite population, and it gives you the mean and the standard deviation. Okay, then you have this handout, correct? You don't need to look at yours. You're going to have this handout. And it looks just like this. Do you remember having this right before your test? Okay, so the mean of the sampling distribution of x bars is equal to the true mean of the population. The mean of the sampling distribution of all the x bars equals the mean of the population. Same thing for proportions. The mean of all the proportions equals the proportion from the population. Your standard deviation. This is where you were introduced to the 10% condition. When do you need the 10% condition? Right. When you don't replace. If I replace, then isn't every time I draw or whatever it is that I'm drawing, isn't it all independent? Because I'm putting it back. But if you don't replace, you got to have the 10% condition. And here is your standard deviation for P's on your formula sheet, correct? Back. Yeah, back, top. And those are both your standard deviations, which is weird to group them that way. But that's the standard deviation of your mean and of means, and a standard deviation of your proportions are both on the back. Normal. Make sure you have this straight. If we're means, we're normal if they tell us the population is normal or the central limit theorem. But what about proportions? Proportion is your NP and NQ have to be bigger than 10. Make sure you have that straight in your mind, because if you are on a proportion problem and you cite the central limit theorem, what's going to happen? They're gonna tear you up. But don't you think, like, when I think of proportions, I think of like 3 out of 15 or 4 out of 10. Like, that's not necessarily this. I don't think of this continuous curve. Do y'all? For proportions? I don't. So if I want that to be normal, then this has to be true. But when I think of means, like, I think of averages, like your average weight or your average shoe size, or things that are the average volume in a milk container. I think of continuous things. So that makes me think we're already here, so I just need to make sure those two. Parameters, statistics. Oh, hold on. Let's try that again. There we go. Okay. Parameters, statistics. There's your sampling. See your sub numbers. Change based on, oh, this was a great multiple choice question. Your standard deviation changes on your sample size, not your population size. Why? Look at the top back of your formula sheet. What information goes into that formula? Sample size. Look at your N. Does that formula have anything to do with the population size? There was a problem on your test, and it was like the population of one of them was like 2,000 students, and the other one was like 5,000 students. And then we were going to take a sample of 100, and he was going to take a sample of 100. And a lot of people picked this because you said, oh, the population size is bigger, so it's got to be a much more accurate. And that's not the case. If you up your sample size, your standard deviation should get bigger or smaller? Smaller, because your data should get more tight, should get more true. Okay. If you are asked to find a probability, you must justify that it's a normal distribution. You must, and how do you do that? Yeah, either this if it's means, or that's if it's a proportion. Okay, cool. Regardless of the shape of the population distribution as the sample size n increases, okay, these are great. These are fantastic multiple choice questions. Okay, so as your sample size increases, the shape and the distribution, the shape of the distribution of X bar becomes more symmetrical and more bell-shaped. It becomes more normal. The center of the distribution does not change. The spread decreases and the distribution becomes more peaked. Sampling distribution of a sample proportion. We talked about this guy. We didn't do the 1 minus P. We did PQ over N. And again, if it's sample information, they should have hats on them. There he is again. Oh, wait. Was there something else down there? No. Okay. What are we doing now? What is this? 2 samples, right? This says on the formula sheet, but it looks different. It actually doesn't. It is exactly that. If you'll look at the back bottom of your formula sheet, it even says difference of sample proportions, and it looks just like that. Okay, so let's look at example 19. The GPAs of graduating students at a large university are normally distributed with a mean GPA of 2.8 and a standard deviation of 0.5. A random sample of 50 students is taken from all graduating students. How many samples do we have? How many samples do we have? We only have 1 sample. Yeah, 1 sample. Just wanted to clarify. We have 1 sample. Find the probability. So I'm talking area under the curve. That the mean GPA of the sampled students is above a 3.0. So first, what do we have to say? Are we normal? Are we normal? Why? It doesn't say so. Does it say normally? It does say normally distributed. Also, CLT, because we have 50 students. So we're doubly good. I also wrote that my N is bigger than 50. God, every time. That my N is bigger than 50. Hold on. Here we go. Okay. Find the probability. Okay, so I know I want a normal CDF. I want to go from 3.0 to infinity. Technically, I guess it should go to 4.0, but you don't know if this is weighted or not. So just go to infinity to be safe. Who is the 2.8? The mean. What do you think is a massive common mistake right here? What do you think is a massive common mistake right there? What do you think people would put right there as their standard deviation? 0.5. Why do we not? Because we have a sample size, right? That 0.5 is what? The standard deviation for who? The population. I need my standard deviation for my sample. So that's why I have to do this. And you would show the formula and plug your numbers in and show them the answer. And that's the number that goes there. So then you would write a nice little sentence about 0.234% of the sampled students would have a mean GPA of above a 30, or would have a GPA of above a 30. Find the probability that the mean GPA of sample students is between a 2.7 and a 3.0. So I'm normal CDF from a 2.7 to a 3.0, and everything else stays the same. The mean of my sample is the mean of the population. But my standard deviation of my sample is not the standard deviation of my population. I have to use my formula. So 91.9%, that's pretty good. 92% of the sample students is a GPA of over a 2.7, between 2.7 and a 3.0. Pretty good. Okay, all right. What is that? It's a 2-sample mean and a 2-sample standard deviation. So 2-sample mean, and this is the difference between two means, I just subtract the two population means. But for my standard deviation, and does this make sense now? Because when we had this before, so what's new to this? Because we are not population data anymore, we are now a sample. So I have to include my sample sizes. And that's on your formula sheet on the back, underneath where it says 2-sample. That's where he lives, so he's always there for you. And that's it. So your homework is page 196. You're doing 2, 3, 4, and 10. And then you've got a worksheet. The worksheet has 15 multiple choice and 3 free response. This is a huge chunk of what's going to be on your AP test. So you need to really, really, really put some good effort into this homework. Okay?